Hello. In this tutorial, we're going to analyze a braced frame, as you see in this picture, in this sketch. The dimensions are given. It's a like two-story level frame structure, but we're just going to analyze one frame of it. And we assume that there were two lateral point loads acting on two upper joints at D and E. And all the joints are pinned. There are two hinges supporting the whole frame. So what we need to do first is to get started with drafting the frame. So I just drafted this frame by drawing each element as a separate line. And that's all we need to do. And no additional point or vector is needed. So we get started with transferring the geometry of the brace frame to the grasshopper environment. So I'm going to call the geometry parameter and then set multiple geometries. And I'm going to select the entire frame and hit enter. Now, getting started with Karamba, we need to drop three components onto the canvas. First is assemble model, where you actually assemble your definition of elements, supports, loads. And then the next one is create linear elements that let us define this geometry as linear elements that is going to be analyzed with Karamba engine. Here we go. And then the next element is support. We're going to have two supports, two hinges. So I'm going to copy this and duplicate the supports. The definition of a hinge requires us to restrict movement, any sort of translational movement along X, Y, Z, and also rotational movements about X, about Z, but allowing rotation about Y axis. So that would be the case also for the next support. We can also pick one support, have one support component and connect 2 points to it. But for like easy definition, we just drop two support components. Now we have a list of points giving us the 6 joints of this braced frame. And we want to extract the support points by list item. I'm going to connect the list of the points, and then I'm going to drop a panel giving the index of the point. I think index 0 will give me the first point. When I click on the list item, the corresponding point will get green on the Rhino viewport. You can check that for your own model based on how you drew your Rhino model. The index value for your model might be different. It might be 2, 3, 4, something between 0 to 5. So you're going to connect this point, which is here for my case, 0, 0, 0, to the position of the support. And then I'm going to extract another list item, connect the points to it, and give the index value. This time I think 2 will be the next one. Again, I click on it and this will be second. This will be there. If, for example, I enter 1, then you see a different joint gets highlighted. That says, well, this is not the correct position of the support, so I will change the position to index 2, and then I will connect it to the support. Then I'm going to connect both supports to assemble model. And then the next step is defining loads. So I go to the load drop-down list and drop new loads. Since we're going to have 2 lateral point loads, I'm going to duplicate this load component, and concentrated load actually gives us point loads. First of all, I'm going to give it a name, F1, and then define the force vector. Since the force is parallel to the x-axis, I'm going to drop a unit x to give the right direction, and then I should give it a factor that defines the magnitude of that point load. So in our case, we had -3 because the point is toward the negative direction of the x, and there we go. And we're going to make sure that the orientation of the load is set to global. So then the x direction will be the global x axis in the Cartesian coordinate system. Then I need to say at which point I'm going to apply this force. So again, this time I'm going to itemize the elements. So I'm going to drop element item and then connect the list of the elements. I have 1, 2, 3, 4, 5, 6, 7, 8 elements. So I'm going to say which element. I think this should be probably item 2. Well, let's check that. If you click on this list item, you won't get it. You can't see where your point or where the load is applied. The only way to see the position of the point load is connect the load to the assembled model, and then from the results, drag and drop the model view. It's a good practice to always drag and drop the model view and view your model as you make it. So this here, under display options, you see that the loads are checked. And then here you're going to have just one point load. So now you see that this is a point load getting applied to the right position and the right element. Also, we should give it a position at which end of it we want to apply it. But let me just show you if the index item was not 2. For example, take 1, then it shows this element. So 2 was this element, this horizontal element, and 1 is this. I can pick any of the 2. But here, you see that the position is just right in the middle of the element. So I should say, bring this point load to this end. For that, I need to give the t position. T position is a number between 0 to 1, defining the location of the point of application along the length of the beam. So if I say 0, the 0 point for this beam is here. So I will change it to the other end, which is 1. Again, based on how you drew your model, for you, if you put 0, I mean, 0 might be here and 1 might be here. It really depends in the order that you drafted your Rhine model. So the next point load is a -5. But based on the sketch, this point load we're supposed to get applied here. So again, I should change the position here. I think number 5, 3. Where is it? Here, not right. 1 here. 3, 4. There we go. So 4 is this. 4 is here. Okay, good. We're all set. So -3 at this point. I'm going to copy this part, place it here. So now this time, index 1 is going to work. This time I changed the name of the force to F2. And then lowercase F2. And the vector this time is -5. And the T position is here. Now I'm going to add this load case by holding the shift to a sample model. And I'm going to flatten all the elements, supports, and loads. Then still, I'm not going to see F2 because here on the result selection, there are two options here. So I switch to F2 and I see that the position is not correct because I forgot to change the orientation to global. So when I say global, then F2 will move here. Now, Karamba needs a definition to consider both of the point loads at the same time and analyze the brace frame under the two loads together. So I go to the load drop-down list, drop load case combination setting, and drop load case combinator. So I define load case FT, F total, as a load case. And then I define the equation. So I say Ft equals F1 plus F2. Make sure you're consistent with typing the name of the load cases because Karamba is case sensitive when reading the equations. Now I need to connect these two components to the load input as well. Everything is flattened, and here the load case combination is connected. And there, here, when we come to the model view under the result selection, I will see FT load case will pop up. Now, if I move to FT, I can see both point loads. Okay, we're all set with the assembling the model, and now we can drag and drop the analyze component from the algorithm and then connect model to model. And then now I connect the analyze model to model view. Now I can see the displaced, the deformed frame, the deformation here. Also, I can see the reactions. As I explained in the previous tutorial, these are like visual scales. So it doesn't affect the numerical value of the reactions, but I can play around with them and get the right value. So here we have a downward reaction here, an upward reaction of 8.8 here. And for the horizontal reaction, we're going to have almost 8 in the positive direction of X. And this little discrepancy refers to the displacement in the frame. So we're all set with getting the reactions. Now, in the next step, we want to actually see the loads in each element. So we go to the results, drag and drop the beam view. I connect this model where I picked FT here and connect it to the beam view. And then here, I open up these two drop-down lists. Here you see this cross-section. I'm going to check it off. I don't want to see the cross-sections because I didn't define any cross-section, and Karamba is going by to just visualize the default. Now I want to see the forces here. First of all, I'm going to turn off this preview. And here I'm going to pick normal X, this force. This normal X represent the axial forces in the elements. And I'm going to here say fill and check the numbers. Now, if you look at the front view, you can see that the magnitude of the axial forces in each member, for example, in this diagonal member, is displayed as a diagram. And this is the value is given 10.21. Okay. And of course, I can play around with the scale of representation here, um, the display scale, but it doesn't affect the value. Also here, you see that the amount of load is minus 2.99 or minus 3. And also the color, the two colors define whether the member is under tension or compression. Blue for tension, um, orange or red for compression. Something that you should remember is that if you connect the analyzed model to beam view, then you'll see you'll get a different axial force here. And that's because the analyzed model goes with the first load case, okay? So here, the default result selection is F1 when you get the output from the analyzed model. But if you get the model from model view, where you actually here set which load combination you want to look at and you set it to FT, if you get this, then the result selection is all about FT. So you will get the axial force related to both of the launch loads. So you will see a different value here. So make sure you connect model view to beam view, and then you're all set with getting the axial forces in your brace frame.